and welcome back. I'm Martina Vettoretti. I'm a researcher at the Department of Information Engineering of University of Padova. And it's my pleasure today to introduce this session of oral presentations on the topic of biomedical signal and image processing. Today the chairs are Roberto Sassi from University of Milan, Manuela Ferrario from Politecnico di Milano, and Gabriele Arnulfo from University of Genova. So I leave the floor to the session chair.
Thank you very much and welcome everybody. So the session is split in two parts. The first one is this morning with 4 talks and the other in the afternoon. So please come back. And so we start with the paper entitled Development of a Novel Surface-Based Approach to Quantify FNIRS fMRI Spatial Correspondence. And we ask Augusto Lauri to come here. We kindly ask the speakers to be very close to the microphone. It was very difficult to hear in the morning, so even if you hear your voice, please stay very close to the microphone, closer than what you're doing. Thank you very much. Okay. You can remove it. Thank you very much.
Okay. Perfect. Thanks you for the introduction. So now we're talking about FNIRS to fMRI integration.
Arrow down. Arrow down. No, on the remote.
Arrow down per andare avanti. Ok, grazie.
There was a small technical problem. 1 second.
Okay, so fMRI is the gold standard for functional neuroimaging techniques given its high spatial resolution and other features, but compared to functional near-infrared spectroscopy, this technique lacks for a direct measurement of oxygenated and deoxygenated hemoglobin, and mostly it cannot be performed in ecological acquisition settings such as an open environment. So in literature we find examples of FNIRS to fMRI integration mostly by assessing their temporal correspondence either on simultaneous or non-simultaneous acquisition. But most of the time we often find a lack of an actual quantitative assessment of spatial correspondence between these techniques. And moreover, there are a wide variety of methods for defining common regions of interest between FNIRS and fMRI datasets that therefore requires to find more objective methods to do this task. And so in this study, we firstly propose a novel surface-based approach for FNIRS to fMRI data integration and analysis. Next, moving to the reliability assessment of FNIRS measurements with respect to fMRI to compute their spatial correspondence and the traditional temporal correlation. So we employed non-simultaneous FNIRS to fMRI acquisitions performed over 18 healthy young adults For the fMRI, we employed a 3D high-resolution MP-radius sequence, followed by a multi-band gradient echo functional sequence. And for the FNIRS, we have employed a continuous wave system with 32 sources and 32 detectors, allowing to have 102 measurement channels that overall allows to cover the entire scalp of the subject. And so in two different sections, they every subject performed a motor task, block design motor task, which is highly employed in both FNIRS and fMRI literature to elicit a motor activation due to its simplicity, and requires participants to either move their left or right hand by pressing or releasing a rubber ball for 10 seconds, followed by 20 seconds of rest. And so FNIRS fMRI data were preprocessed into FreeSurfer, while FNIRS signals were imported into Brainstorm, which is a MATLAB-based application. And it's important to say that the 3D MP-radius sequence was used as an anatomical template referred both to fMRI data and FNIRS data to have, as we will see shortly after, a common reference of anatomical structures and cortical surface, especially. Indeed, fMRI data were firstly motion corrected, Gaussian smoothed, and then in FreeSurfer they were projected onto the cortical surface, next to be imported through custom scripts we have made into the Brainstorm environment. As well, FNIRS data were motion corrected, bandpass filtered, and next projected onto cortical surface by FNIRS image reconstruction by an algorithm called depth-weighted minimum norm estimate algorithm. And so at this step, we have allows us to have a one-to-one correspondence between FNIRS signals and fMRI signals onto the cortical surface. So a vertex-wise correspondence between cortical meshes, and also allows us to perform the same analysis in the same environment, which in this case is represented by the Brainstorm environment. And so our approach is intrinsically surface-based because we are referring all the analysis to the cortical surface. And the first steps requires to compute the statistical activation maps to basically contrast left and right hand movements through GLM analysis, both at the subject and the group level, to obtain t-value thresholded maps for statistical significance, acting as functional ROIs, acting as functional regions of interest. Next, we impose an anatomical constraint depending on the task we are doing. So since we are dealing with a motor task, we consider, for example, the precentral and postcentral areas derived from the Desikan Kilani atlas, but keep in mind that depending on the task and the available neuroimaging atlases, this approach can be extended to any kind of data set. And at the end, we compute the so-called, what we call it, anatomically constrained functional regions of interest by intersecting anatomical and functional regions of interest, and therefore performing a following reliability assessment to basically have a comparison on FNIRS and fMRI significant activation on common regions. And so for the spatial agreement, we computed the dice coefficient over these regions of interest to obtain this measurement of the actual spatial agreement between these two techniques. So basically, it's a ratio between the cortical areas. And here are some results where we highlighted with the gray level, with the gray squares, the regions that are contralateral to the hand performing the task. For the motor task, we expect to find the most significant cortical activation. And we observe a moderate to substantial spatial agreement at the subject level, both concerning the comparison of FNIRS with, in red, oxygenated hemoglobin and in blue, deoxygenated hemoglobin. And these results are confirmed also at the group level when comparing data with the oxyhemoglobin. However, lower levels of agreement are found when comparing fMRI to deoxygenated hemoglobin. And so, in line with current literature, we also assessed that we are able to assess the temporal correlation between signals, and this was done over the anatomically constrained functional regions of interest we have found so far between block average responses. So the mean response, for example, to the right hand movement in those 30 seconds following the stimulus onset. And very briefly, results hopefully are in line with current literature, indicating both for the comparison with oxy and deoxyhemoglobin that there is a moderate to strong temporal correlation at the subject level. This correlation is even increased up to strong temporal correlation when moving at the group level analysis. So, very briefly, to sum up our reliability assessment, even if we just employed a very simple but robust motor task, reveals that there is an established spatial and temporal correspondence between fNIRS and fMRI. And in turn, the analysis we have proposed can be promoted can promote the translation of can be applied, to other data sets in order to promote the translation or even the adaptation of fMRI task in fNIRS routine, but in ecological settings as fNIRS allows to do. And compared to current integration studies, our surface-based approach allows to have a direct comparison as vertex-wise correspondence indeed between fNIRS fMRI dataset by projecting individual source maps onto a common anatomical structures, which is the cortical surface, as well having an objective definition of cortical regions of interest that only depends on the statistical threshold level we set for computing activation maps, as well as just the selection of cortical parcellation of interest depending on the task and also our research question. And in turn, this approach may increase the reproducibility of analysis, such as employing different data sets, having the same cortical regions of interest shared across data set or even studies for reproducibility. And needless to say that future works will need the necessity to also look to other functional tasks, translate indeed other functional tasks, and apply that to even simultaneous, since it was not possible, simultaneous fNIRS to fMRI data sets to increase basically to corroborate the results we have obtained. And with that, I conclude. Thank you for the attention.
We call to the floor the next speaker, Elena Lidi, with a talk entitled Supervised Learning-Based Detection of Pressure-Induced Failure in Continuous Glucose Sensor.
Okay, so thank you for the introduction. I'm Elena Lidi from the University of Padova, and today I'm going to present this supervised approach for the detection of pressure-induced failures in continuous glucose sensors that are sensors mainly used for the management of type 1 diabetes. Okay, so type 1 diabetes is a chronic metabolic disease that is characterized by the lacking production of insulin, that is a crucial hormone for the regulation of glucose in blood. Subjects with type 1 diabetes must adhere to highly demanding guidelines that consist in a lot of daily actions. For example, subjects have to estimate the amount of carbohydrate they are going to eat, they have to follow a diet regimen, they have to compute an optimal dose of insulin, and in particular they have to monitor their glycemia. So they have to monitor the blood glucose concentrations. And this is possible thanks to the use of particular sensors that are called continuous glucose monitors, or briefly CGMs. So continuous glucose monitors are minimally invasive sensors that allow to the subject with diabetes to monitor their glycemia in everyday life, but also in every moment of their life, by providing new measurements every 1 to 5 minutes. So the glucose sensors is actually not the thing we see, because it is placed on a needle that is inserted in the subcutis. And here it measures an electrical current that is generated by a metabolic reaction, that is the glucose oxidation. So the current is then converted into a glucose concentration and can be transmitted to a portable receiver. So for example, the sensors can be connected to smartphones or smartwatches, and in this way, subjects can easily monitor their glycemia in every moment. But these sensors are proven to have a strong impact also on the clinical practice, because clinicians can use them retrospectively by analyzing offline the glycemic profile of their patients. And in this way, they can evaluate the effectiveness of the treatment, they can adjust the therapy, or just suggest personalized dose. So these sensors can be affected by faults or artifacts, and in this work we focus on compression artifacts that are also known as pressure-induced sensor attenuations. These failures are temporary faults of the sensor due to the application of a mechanical pressure on the device or on the surrounding area. So for example, the subjects while sleeping can sleep on the sensor or roll on the sensor, and the mechanical compression of the device can reduce the blood flow in the sensing area. So the compression artifact results in an underestimation of glucose level for about 40 to 50 minutes. And in the figure, there's the typical shape of this artifact that are characterized by a drop in glucose level followed by a restoration phase when the pressure is released. So artifacts can lead to misleading indication that a hypoglycemic episode has occurred, and hypoglycemia is a very risky situation for the patient because can be associated to, when untreated, can be associated with coma and also death. So one of the risks associated with this artifact is that clinicians, when evaluating the traces offline, can suggest suboptimal therapy adjustment to compensate for the presence of many hypoglycemia. So the aim of our study is the development of a fault detection approach for the retrospective recognition of these artifacts using supervised classification algorithms. But where's the novelty of this approach? The supervised approaches for detecting these artifacts are not investigated in literature. In fact, at the state of art are available only 2 strategies. The first is called rule-based approach, because use the definition of threshold and heuristics to detect the faults, but these approaches can be oversimplified, so difficult to generalize. On the other side are available model-based approaches that leverages on the identification of a model to describe the patient's physiology, but this approach require multiple inputs that can be unavailable sometimes, for example, the carbohydrate assumption. So this is the pipeline of our study. The first step is the simulation for data collection. Then there's the methodology, the core of our work, that is the supervised detection, that is composed of 2 steps. The first is the feature extraction. So we define features that are created specifically for this problem. And then we apply the supervised classifier. And finally, we evaluate the results. To develop a fault detection approach, we need a dataset that contains information about the failure. So we need to know when a fault starts and when, for example, a fault ends. But accurate collection of faulty data requires dedicated experiments that are hard to perform in practice because these artifacts can be difficult to induce or can require the a posteriori manual labeling on collected data. And this process can be expensive and uncertain. So an alternative is to use simulated in silico data, and for this work we use a very powerful tool that is a UVA Padova type 1 diabetes simulator. That is a simulator that is also approved by the FDA as a substitute to the animal trials before the clinical trials. So we use this tool to simulate 10 days of monitoring for a population of 100 virtual subjects, and then we generate the artifacts. We simulate them as additive components using a model validated on real data. So in this way, we obtain 10 days of simulation for 100 subjects, and each glycemic profile is corrupted with a random number of folds with a random duration located in random positions, for example. So one of the key steps of this approach is the feature extraction, because we need to define features that account for the typical shape of the artifacts and their rapid dynamics. So we decide to define manually 3 features. We can see the effectiveness of this feature in the figure. Here is reported a CGM trace that is colored according to the value of the feature. With the dashed line is highlighted the faulty portion, and we can see that the red color is associated to faults. And this happens for all the 3 features. So this is actually the dataset represented in the feature space. I reported as red crosses the faulty data, so the compression artifacts, and as black circle the normal data. So we can see that these 2 clouds can be distinguishable. After the definition of the feature, we can apply the supervised classifier. We test multiple well-established methods, and we switch from anomaly detection problem to a binary classification problem. So for example, we define as label 0 the normal status of the sensor, and with label 1 the faulty status. To evaluate the results, we need to define the true positive, the false negative, and the false positive. So for example, the true positive are highlighted with the green band and are all the compression artifacts that we are able to identify. The false negative are the artifacts that we are not able to identify, so for example, the one in the red band. And the false positive are all the portion of the signal that were detected as faulty, but actually is normally working. The evaluation metrics we use are the recalls, so the fraction of compression artifact we are able to detect, and the number of false positives per day. These are the results. On the left, there's the visual representation of the results achieved with random forest. And with this algorithm, we are able to detect the 90% of the failure, and at the same time, we generate, on average, 1 false positive in the 10 days of monitoring. We can also compare the results with the baseline approach, that is the rule-based approach. We can see that with this state-of-art method, we achieve lower recall and a higher number of false positives per day. So in conclusion, we see that continuous glucose monitors are a crucial sensor for the management of type 1 diabetes, and compression artifacts are one of the most common failures of the sensor. In this work, we develop a supervised approach for the retrospective identification of compression artifacts by testing multiple classifiers and achieving promising results. Future work will investigate the application of this approach on real data, for example, and the development of fault detection approach that can work on real time. So I want to thank you for your attention.
Thank you very much. We move to our next talk. We invite Roberta Saputo here to the podium. She will present a paper entitled Assessment of Cerebral Autoregulation in Patients Undergoing Anesthesia with Propofol, a Comparison Among Spontaneous Variability Methods. Thank you very much.
Good morning, everybody. I'm Roberta Saputo, Biomedical Research Collaborator at the Department of Engineering of the University of Palermo. I'm honored to be here today at the 8th National Congress of Engineering in order to exhibit my first scientific work in collaboration with the University of Milan and Policlinico San Donato. Our study proposed a comparison of spontaneous variability method for assessing cerebral autoregulation in patients undergoing general anesthesia. Cerebral autoregulation is a physiological mechanism that maintains cerebral blood flow within a constant range despite blood pressure variations. The assessment of cerebral autoregulation can be carried out through a dynamic method by measuring the response of cerebral blood flow to spontaneous rapid change in arterial pressure. The use of the transcranial Doppler ultrasound technique allowed assessment of this dynamic cerebral autoregulation, assuming that cerebral blood flow velocity is a good surrogate of cerebral blood flow. The non-invasive characterization of dynamic cerebral autoregulation is based on the study of a dynamic bit-to-bit closed-loop interaction between mean arterial pressure and cerebral blood flow velocity, considering the link between the mean arterial pressure to cerebral blood flow velocity, also known as a pressure-to-flow link. In this context, this study aims to compare two different aspects, two different methods of assessing cerebrovascular physiology, such as autoregulation index that ranks the efficiency of autoregulation capacity, and dynamic information measures in order to compare, study the dynamic interaction along the pressure-to-flow link. The question is whether the two investigated methods are sensitive to similar or different aspects of cerebrovascular physiology. The case studies in which the analysis were conducted involves 18 subjects scheduled for artery coronary bypass graft surgery and enrolled at the San Donato hospitals. The subjects were studied into experimental conditions such as before induction of general anesthesia in spontaneous breathing and during general anesthesia in mechanical breathing. The experimental protocol involves two sections of continuous and spontaneous and synchronous acquisition of biomedical signals, such as arterial pressure, derived invasively with a catheter insert into the radial artery, and cerebral blood flow velocity with a Doppler ultrasound device. After the acquisition phase, two time series, stationary time series, were extracted, such as mean arterial pressure and mean cerebral blood flow velocity. We select analyze the window of 250 bits. The first method of analysis is the autoregulation index, computed with a parametric estimation. This method models the response of mean cerebral blood flow velocity due to spontaneous change in arterial blood pressure. By using a second-order filter model, known as a TX model, in which the input is the normalized mean arterial pressure and the output the mean cerebral blood flow velocity. The models, by combining the three parameters of these models, such as the gain kappa, the time constant T, and the damping factor D, the model returns 10 curves of mean cerebral blood flow velocity, named as step responses, corresponding to 10 curves of ARI. ARI values ranks the efficiency of the autoregulation capacity. In particular, ARI equal to 0 indicated an absent autoregulation, lower than equal to 4 indicated impaired autoregulation, and higher to 4 a good autoregulation, and ARI equal to 9, an excellent autoregulation. According to this parametric estimation, the 10 F curves derived from the TX model were compared with the 10 F curves derived using an autocrossive regressive model. And the comparison is evaluated using the normalized mean square prediction error. And finally, we select the optimal I that corresponding to the minimum value of this norm. The second method of analysis is the dynamic information measures for beverage system. Given a beverage system, which M is the driver and F is the target system, the framework of the information measures allow to assess, to quantify the information content of a target system in terms of predictive information, such as the information contained in the target system that can be predicted by the past of the entire process. The predicted information is evaluated as a sum of cross entropy and internal entropy. And under the assumption of the joint Gaussianity, these dynamic information were evaluated using model-based estimators. The figures show the distribution of I-values computed using a parametric estimation of the autoregulation index in the pre-post conditions. The significant differences between the two experimental conditions were evaluated using a statistical test, such as the Paired-Wilcoxon-Singh-de-Rank test, with a significance level of 5%. The result of this method suggests that the autoregulation remain intact during the pre-post protocol, confirming that the propofol general anesthesia doesn't affect the autoregulation. In contrast, the result of dynamic information measures evidenced an increase in cross entropy, and these results suggest that is indicative of an increased of cerebrovascular coupling, and that indicated a reduced cerebral autoregulation capacity. Finally, the two methods investigated were compared with the Spearman correlation index. The correlation is a weak correlation, and this result confirmed that the high dynamic entropy measures provide different information on the cerebrovascular control and on the functioning of the autoregulation. In conclusion, the ARI method suggests that the autoregulation remain intact during the pre-post protocol in this group of patients, while the dynamic cross entropy in post suggests that the increase of dynamic cross entropy in post suggests that the dynamic of cerebral autoregulation becomes more dependent on the systemic pressure. This indicates a possible alteration of the autoregulation mechanism. In conclusion, the two investigated methods highlight different aspects of the cerebrovascular physiology. Future studies aim to investigate the cerebrovascular interaction, considering the effect of the cerebrovascular, the cerebral blood flow from cerebral blood flow to arterial pressure, and to quantify such interaction in the frequency domain. Thank you for your kind attention.
Okay, we introduced the last speaker, Michael Lassi, and the title of the talk is Early Stage of Cognitive Decline are Characterized by Different EEG Microstate Dynamics. Thank you.
Hello, everybody. I'm Michael Lassi from the Scuola Superiore Sant'Anna of Pisa, and today we'll briefly present our study on the identification of markers of early stages of cognitive decline from resting state EEG. So as you probably know, Alzheimer's disease is the most common cause of dementia worldwide, and it affects every aspect of the patient's lives. And it's a form of cognitive decline that is related to the formation in the brain of neurofibrillary tangles and of amyloid beta plaques. But Alzheimer's disease does not happen abruptly, immediately, but is thought to be a part of a continuum in which the neurobiological changes that bring the symptoms may start even decades earlier than the first appearance of the symptoms themselves. So it's important to define some clinical stages that can be used to assess and early detect the possibility of developing Alzheimer's disease. And among these stages, there are two that are clinically relevant, that are the mild cognitive impairment condition, in which that is the first clinical condition in which you can observe in a patient a clinical objective cognitive decline. And then there is subjective cognitive decline that is especially important because it's the first case in which the patient self-refers to the hospital because they claim to have a memory or other cognitive impairment, but in reality, at least objectively, when screened with a cognitive test, they appear to be cognitively normal. But literature shows and clinical studies show that subjective cognitive decline patients have a higher chance of developing dementia than the healthy aging condition. And so this is our target population to study some markers that can we use to develop and to detect the development of dementia later on in their lives. Current markers of Alzheimer's are either costly or invasive to collect, since they rely on the acquisition of structural images such as PET images or MRI images, or they require the collection of cerebrospinal fluid biomarkers, so a lumbar puncture is needed to collect these samples. And so we asked ourselves whether it is possible to identify from resting state EEG signals some markers that can distinguish these cognitive decline phases and successively define markers that can detect the onset of Alzheimer's. And this is part of the preview project, which aims is to identify those markers in the EEG signals. So first, what we did was to recruit patients, about 50 patients with subjective cognitive decline, about 50 with mild cognitive impairment, and a group of healthy controls. And after defining their cognitive status, we collected their resting state EEG for about 20 minutes with a 64 electrode cap. And after preprocessing, and also we also collected from a subset of these patients their cerebrospinal fluid biomarkers to check whether they really have an undergoing Alzheimer's disease markers. After collecting their EEG, so we started the quest for identifying possible markers, and so we started with a very simple spectral analysis in which we splitted the power spectrum of the EEG signals into 4 frequency bands of interest and 6 regions of interest over the scalp. And actually the results that are shown on the right display that there are little but significant, there is a little but significant increase of delta power activity in mild cognitive impairment patients with respect to healthy controls. And this is in line with what the literature says. But actually, we didn't find any difference between, for example, subjective cognitive decline patients and healthy controls. So we wanted to do more. And to do this, we applied this technique called microstate analysis that I will briefly explain, since it's not so common. Microstates are quasi-stable topographies in the EEG signal. That means that if you look at the time point in the EEG, and you plot its voltage topography, and you do it several times, you will see that the topographies that appear over time are a few, and they are repeated over time. And these repeated topographies are called microstates. And the other property of microstates is that this topography is stable for 60 to 120 milliseconds, meaning that the time course of the EEG can be summarized in some way by a sequence of discrete microstates. And so what we did was to extract this microstate from our EEG signals by means of K-means clustering technique from each subject separately. So we obtain a set of microstate topographies for each subject, and then we clustered again to obtain a grand average topographies. And from these grand average topographies, we can then reconstruct the EEG signals of each subject as a sequence of these microstates. And then what we did was to look for differences both among the topographies themselves in the diagnostic groups and in the temporal dynamics of the microstates. So we started with the analysis of the topographies themselves. Typically in the literature, 4 topographies are identified as in a healthy condition, at least at rest. And we also identified 4 topographies similar to the ones that are described in literature, that are the grand average topographies are displayed here. And we used this topographical analysis of variant test to compare the topographies among the diagnostic groups. And unfortunately, again, we didn't find any significant difference among healthy controls, SCD, and MCI patients. But luckily, the microstate dynamics, the sequence of microstates over time, displayed several differences. And we observed them by extracting some metrics that summarize the sequence, that are the average microstate duration, the microstate occurrence per second, so their frequency basically, the transition probability from one microstate to another, and then some nonlinear properties such as the Lempel-Ziv complexity of the sequence. So we aim to evaluate the repetitiveness of the sequence, and the Hurst exponent, meaning that is an index in, telling us whether the sequence is a random walk or is structured. And what we found, and can be kind of observed also visually, these are 2 EEG sequences, microstate sequences for 1 exemplar SCD subject and 1 MCI subject for 2 seconds. And if you observe the sequence of the SCD subject, you can maybe see that the microstate sequence is a little bit more varied, and there are some microstates that appear more than in the MCI subjects. And that's what we quantified with the extracted metrics. So we found that the microstate C is significantly altered in its duration over the evolution of cognitive decline, meaning that from the healthy condition, they have the higher duration of microstate C, and then it decreases over SCD and MCI patients. And the frequency of occurrence of the microstate B increases in MCI patients compared to the SCD ones. And also the transition probabilities reflect these differences in the sense that microstate C tends to receive less inputs from the other microstates in the pathological conditions. And the complexity of the sequence over time changes. In the pathological MCI condition, there is a less complex sequence of microstates with respect to NCD. And also the Hurst exponent tells us that the sequence tends to be more towards a random walk with respect to healthy controls and SCD. And finally, we wanted also to check whether these microstate topographies are related to the underlying pathology. Up to now, we also only assessed the cognitive aspect, and now we instead compared the topographies by looking at the pathological cerebrospinal fluid markers of the disease. And basically, there are 3 markers from the cerebrospinal fluid that are called beta amyloid, phosphorylated tau, and total tau. And you can create a 3-fold classification ATN based on that. And if the patient is only positive to the A marker, it can have the Alzheimer's disease, but also other form of dementia. And if it is positive to the A marker and the T or N marker, it will have for sure a neurodegeneration in progress. So analyzing the topographies on only A amyloid beta negative and positive subjects, we found no differences again. But when looking for, when looking for the topographies of patients with confirmed Alzheimer's pathology versus non-confirmed Alzheimer's pathologies, we found a significant difference of the microstate C topography. That is also the microstate that change is dynamic most in the previous analysis. So what we can conclude is that basically our spectral analysis cannot be a reliable marker of the disease, and also the microstate topographies cannot, because we didn't find any difference in the cognitive decline evolution. While the microstate dynamics can be used for evaluating the disease evolution, especially in the cognitive terms, and maybe the microstate topography can be used to assess the neurodegeneration. And now what we want to do is obviously using these identified features to create a classifier using machine learning to evaluate whether we can really predict, first in a cross-sectional way and then in a longitudinal way, the evolution of the disease. And then we want also to combine the identified markers at rest with the markers that come from event-related potential, so by recording EEG during a memory or attention task, like the one in the video. And then finally, we want also to build a computational model that relates the synaptic degeneration and the cognitive degeneration following Alzheimer to the microstate that we observe. And finally, we would like also to validate whether the observed microstate degeneration is only specific of Alzheimer or is common to other forms of dementia, such as Parkinson's disease dementia. So this is all. I would like to thank my lab and our clinical colleagues, and I would like to thank you for listening to me.
Thank you very much. I invite now the fourth speaker on the podium so that we can have questions from the audience. And I have a curiosity for the first speaker. So, yes, for Augusto Boni Lauri. So maybe you. Yes, unfortunately, you need to walk to the podium and get the microphone. So, in your protocol, you were, your results were related to the protocol you designed, obviously. So you were asking, if I remember, to squeeze the hand, and then you were, so for 30 seconds, if I remember, or for a certain amount of time, and then there was a rest period. So clearly, you got a certain level of agreement. My curiosity is related to how this level of agreement is linked to the length of the protocol. So if you let's say, if you change the protocol, so you reduce the length of the squeezing, or you put a bit of variability into the protocol, do you think, or did you try, did you verify, do you have any preliminary result or any idea of if this kind of coherence will remain? Because obviously, I think the long-term goal of your activity is also to try to substitute one for the other, one technique with the other. So, and it works well in this specific case. Do you think it's going to be easy to generalize it to other kind of protocols?
I think so. Yes, works. Okay. Yes, thank you for the question. I think it will be reliable also with different durations of the task, and also other tasks which needs to be identified. We choose indeed this motor task because, as I shortly mentioned in the presentation, this task is very reliable to assess an activation both from fMRI and FNIRS point of view. And to be frankly honest, we could have also used a shorter duration, so fewer blocks both in FNIRS and fMRI to basically get the same levels of activations, statistically speaking. So concerning to change the duration of that, I think it would be fine also to shorten in that. Not so much because it's based on repetition, so the statistical power to that will decrease after if we employ too few blocks. For other tasks, it needs to be indeed clarified. We just started also to test it with other functional tasks, like cognitive ones, like the Stroop test, or yes, the Stroop test mostly, and we need to clarify that. But maybe it was too strong to constrain that to the motor regions, but the same approach can be applied even if we want to see, for example, supplementary areas to the task, like, for example, would be like the weak activation we also experience on the visual areas, because indeed they're looking at the screen telling them move the right hand or move the left hand. So future studies will also need to investigate these aspects.
The cognitive part is very interesting.
Yes.
Okay. Thank you very much.
I have a question for you. I think you are the first person. Ciao. Qui.
Okay. Thank you.
So I would like to know some more information about your methodology as regards, for instance, the projection to the cortex. How many cube millimeters you are projecting? Do you think this kind of average as an impact? And also, if you can tell something about a possible specificity or differences with regards, for instance, the contribution of veins or capillaries to your FNIRS signal, since you measure both oxygenated and deoxygenated. So are you planning to, I don't know, to merge with some information about the veins location or something like that?
Well,
so two questions actually, sorry for that.
Yes, the first one on the millimeters, can you repeat it?
Yes, how much you are projecting to the cortical surface?
Yeah, well.
If it has an impact, this kind of average you are doing. No?
Okay. For computational purposes, basically, all the surfaces were initially preprocessed in FreeSurfer, which basically works into the range of 2 to 3 millimeters. So we have parcels, small vertex parcels over the cortical surface that are a few millimeters, like 2 to 3 millimeters, more or less. So we are looking at a set of signals which everyone samples basically 2 to 3 millimeters of the cortex. So to get an idea of how much we can change, we are working on the projection of data of fMRI and FNIRS. Concerning the processing of FNIRS data to get excluded from the hemodynamic components basically is dealt within the FNIRS itself, because the FNIRS indeed has a diffusive information, so it captures signals coming from also extracerebral layers, and the preprocessing now was very simple because data were quite good, but can be get out from regressions with like additional measurements like short channel separations that get rid of the hemodynamic components from the signal itself. So the contribution, it does not need to have actually to tackle the actual position of arteries and veins and capillaries of that, because for the FNIRS signals, these artifacts are dealt with the processing itself by getting rid of these components to the signal itself. While for fMRI, it's a volumetric one, so a volumetric signal, so we do not need to cope with this aspect.
Yes, I was wondering. Yes, I was wondering whether you can somehow take advantage of this kind of complementary information to get more information about localization.
The idea to get the most of that, except for studies that would like to look at the interplays seen by FNIRS and fMRI, but we need to design indeed a simultaneous experiment, is also to translate, to get a method to assess the reliability of some well-established fMRI sequences, translated that into the FNIRS context by also extending that interaction we can have with FNIRS, having a portable device. So getting also traditional experiments also out of the lab to see it in more ecological condition. That's the idea of having a bridge for integrating data and also to analyze that in another context.
So thank you. My question actually is for the last speaker. Thank you for your talk. I was wondering, like this microstate analysis is really based on clustering of peaks in the global field power. So the topographies and so on are really catching what is the difference, if any, in terms of power. So have you ever thought about exploring like methods that allow you to catch differences in other putative mechanisms for, I don't know, brain interaction or brain networks such as face-to-face coupling and so on? And one example being the common and like popular hidden Markov model with time-delayed embedding approach.
So yeah, we explored a bit of connectivity analysis that I didn't present. Actually, it was still spectral related because it was I used the imaginary part of coherency to estimate the connectivity. So yeah, we explored it and we extracted some network metrics from the adjacency matrix of some of the regions of interest that we used. Such as like we extracted the small world index to estimate the ratio between the characteristic path length of the graph and the clustering coefficient. So we tried also this approach a bit. We didn't explore much in depth like effective connectivity such as Granger causality and so on. But yeah, we tried it and we didn't find major differences apart from the small world index in the delta band. So it was still related to a power to the power spectrum.
Okay. But just to follow up on this, so the state, the microstate definition was still based on the standard approach, and then you calculated these metrics on top of the states found by.
Yeah, no, actually it was a completely
different
separate
analysis.
yeah,
Okay.
so, yeah, we didn't mix the two things.
Okay,
yeah.
it's clear. Thank you.
Paolo Magni from University of Pavia. I have a question for Elena about the glucose monitoring. Yeah. Okay, thank you for the presentation. Nice work. I have a short question and comment. You perform a machine learning approach on simulating data. And as we know, and yesterday was remarked very well, that of course results depend on the inputs, then on the simulation. You used a well-known and validated simulator, then a model. But of course, the model is qualified or authorized for a specific application. For example, in your case, you mentioned the possibility to avoid animal experiment. Then you can have a good, can be a good step to have some behavior in human, typical subject variability and so on. But you use this model in another setting for describing this artifact about the monitoring. You have to add this artifact to the model. Then my question is, if you test the robustness, if the model is adequate for the goal that is different for the purpose in which the model was tested, verified, and the efficacy demonstrated. And the second question is if there is in your work in your lab some comparison with some more traditional method, for example, filtering of signal or imposing some regularity on the physiological signal.
Yeah, so thank you for the questions. About the first one, I don't think that I get the point, but I try to say a bit more of information. So the simulator is used for the standard use to simulate glycemic traces, and then it's applied a an additive component to simulate the folds. So the simulator is in its standard use, and the model we use to add this component is validated on other real data, of a more recent study. So our two model, one for the simulator that is well established, and the other model for the artifacts. About the sorry, I forgot the second. Yeah, it's the robustness in the sense. This work is part of a collaboration, so we also have real data to compare the performance, if the performance on the simulated scenario can be comparable to the real scenario, and the work is still ongoing. And I think that one of the problem of applying this type of approach on real data is related to the frequency of the folds. So supervised learning needs a ground truth, so we need a lot of label, like faulty label. For the data we have, this is not a problem because we have enough subjects, so it is tested on real data. There's, as expected, a small degradation of the performance, but this approach can be applied at the same way. So yeah, I've not presented the results on real data, but it's even comparable, I mean. Yeah, we didn't test because we work especially with the real data. The real data we have are only CGM data because the collaboration project is with Dexcom that provide us the data, so we only have CGM data. And for this reason, it's important for us to use only the data of the sensors. So all the filtering part actually is investigated using only the CGM, so it's kind of an autoregressive model. And I don't have the direct comparison. I think that machine learning works a bit well. A bit better, but the comparison with the whole model, so with multi-inputs, carbohydrate, insulin, and CGM, is not performed because we don't have the data, so we don't investigate this thing. It's a different scenario.
Thank you. I have a question for Elena as well, so you can keep the mic. Yeah, I agree with what Paolo said, and my additional curiosity was that you showed these nice 3 handcrafted, expert-driven features, and then a bunch of models that you trained on these 3 features, right? Those were the only inputs to the models, as I understand, right? So my question is, if you started out with a bigger set of features and then did some feature selection that shrinked it down to those 3, or if you didn't do it, why do you need all 3? I mean, is that coming from previous literature or anything? Thank you.
Yeah, this is a part of the feature set, and so because this was the project is still ongoing, so then we add the feature. We develop new features that are still manually extracted, but the main problem is that it's difficult to extract many features when we have just one signal. So we have just the CGM trace, so the glucose concentration profile in time during the 10 days of the subject, that is the average duration of the sensor. So it's difficult to create and invent a lot of features to perform also a feature selection. What we do is, for example, at the end, I think we have 5 features, and we can evaluate which is the most important one, for example, and if, for example, removing some can be correlated or redundant, for example, to remove them for the feature set. But the main reason of the 3 features is that we just have one signal, so it's a bit difficult to to define many of them. We need all three of them, yeah. This is also in the whole feature set of the 5 features the most important, so yeah.
I have a question for Roberta Saputo. So I don't know, it's a curiosity because you don't show the change in blood pressure. Propofol is a vasodilator, so it's can induce a very large change in blood pressure. Do you investigate how large they were, and if there is a relationship with the change in the index that you computed in relation with the change in mean arterial pressure, or if you have some patient with some comorbidities like hypertension, because hypertensive patients are at very risk to go low down with blood pressure after propofol infusion.
Yes, the propofol general anesthesia is the anesthetic propofol induced and depressed the autonomic system. But sometimes, but a lot of papers, a lot of in literature demonstrated that confirmed that these pharmacokinetic properties of these anesthetics don't affect the autoregulation mechanism.
Yes, okay, but if you don't show the values of mean arterial pressure, so you are challenging your the brain autoregulation because you are challenging also the blood pressure because it was supposed to change. So yes, the combination of two are expected to be studied in the next research or something like that.
Future studies could be designed in this sense. And I don't investigate this aspect. Yes.
Okay, thank you.
Thank you.
If we have a minute, I have a question for Michael. So it was very nice, your presentation, and myself, I was not so confident with that method, and I did like it a lot. So, well, first of all, instead of A, B, C, D, I would say A, T, C, G. So it becomes the DNA of your patient. So with that suggestion on the back of my mind, I was thinking about what you could do now. So I'm not 100% convinced that machine learning classifier might be the best way to use those data. So I was wondering if you thought to have some kind of longitudinal studies. For example, you might have a change in the same patient over time. So for example, for rehabilitation or for some sort of monitoring of the progression of the disease, you might want to extract maybe a fingerprint of the whole computation you do. I don't know how complex it is to extract that stuff and if the software is available or it comes from you, but my question was this one. So if together with that great team you have Professor Sorbi, Grippo, and Professor Bessi, if you had in mind to have some studies for this kind of outcome, because I guess also having many data for a machine learning model, for training a machine learning model might be an issue for you. Thank you.
Thank you for the question. Yeah, so we are planning, the project is planned to have a longitudinal study. So basically the subject that we recruited as subjective cognitive decline now in these past 2 years or less will be followed up every year to check their cognitive status and see if there is a difference before with the previous exams. And at the follow-up, we will not collect, unfortunately, the EEG for practical reasons. But so we will just have, on the long term, we will have a label telling us whether the subjective cognitive decline subject of which we have the EEG will have developed the disease in N years. Obviously, this is something that takes quite a few years to happen, since most of the subjects, hopefully, they will not develop the disease, but some of them will develop the disease in 5 to up to 10, 15 years. But yeah, so this is the plan. And what I'd really like to do with the microstate is to check whether actually these differences that we found cross-sectionally will hold longitudinally, because yeah, the hypothesis is that this will be true, but we don't know yet.
Okay. Thank you. Congrats to you and your team.
Thank you.
I have probably there will be just time for a single question. I only have one, if there is no more from the audience for you. And I thank you for your presentation. I mean, I think it's very interesting and the topic is very important, clinically relevant. If I understood correctly, your protocol, the recording protocol stands for 20 minutes resting state activity. And whether you use 20 minutes continuous recording for all the populations, so SCDs, ADs, MCI, and healthy controls. So my first question is, how did you control for sleep and drowsiness? And how do you prevent from that?
Yeah, so the protocol is actually, sorry, the protocol is not just 20 minutes resting state with eyes closed, but it's an alternance between eyes closed and eyes open condition, of which I analyze the eyes closed condition. So, and this is designed, I think it's in some international guidelines, and it's designed to avoid possibly the drowsiness. Obviously, I don't control directly the thing in the signals, at least unless I see something exceptional. But the operator should check also for drowsiness and sleep, obviously. But the design should be robust enough to avoid that by itself.
And I only have one follow-up question: is how do you perform microstates analysis that is significantly correlated by looking at the spatial correlation of power, as you mentioned? How was the pre-processing step conducted for removing channels or replacing bad channels?
So yeah, we use the, again, sorry. Yeah, so we use the a semi-automated pipeline that is a combination of a pipeline that is pretty famous, the PrEP pipeline, that performs basic filtering, the trending, and most importantly, robust average referencing. And then on top of that, we perform an automated ICA decomposition from which artifactual components, especially muscle components and high components, blinking and saccades, are removed automatically from the signal. So then from the components, and then the signal is reconstructed without those independent components. And yeah, so this was the pipeline, more or less. And there was another question.
I mean, specifically for the bad channels, have you
choose
or found bad channels, and whether you found that? I suppose you have found at least one in every subject.
Yeah.
And how you replace that?
Yeah. So the PrEP pipeline handles it automatically, and it combines several steps of bad channel detection inside it. One, for example, like simple thresholding methods with also correlation with nearby channels, and other methods that now I forgot. So, but I think it combines 4 methods and then selects the ones that are always selected as bad channels by all the methods. So
and you remove that, or
it interpolates them with by cubic interpolations.
Thank you very much. Thank you for all for coming here. And it was a pleasure to listen to all the very interesting presentation and your questions. It was a very fruitful discussion, and enjoy the rest of the Congress. I hope to see you this afternoon to continue with the oral session. 3:30. Okay. Thank you very much.
Michele Schiavon from the Department of Information Engineering here in Padova, and
I'm Alessandro Gandin from the Department of Industrial Engineering.
Okay, so the second poster session will be related to 2 tracks. So the track 5, which is biomedical signal and image processing, and track 6, neural engineering and micro and nanotechnologies.
okay, and this is the evaluation committee that will go around the posters. So it is composed by Marta Palazzini from the National Research Council, Laura Stolfi from La Sapienza, University of Rome, and Cristiano De Marchis from the University of Messina. And
Also from Emilia Ambrosini from Polytechnic University of Milano, Alberto Greco from University of Pisa, Gabriele Arnulfo from University of Genova, and Christian Mayburger from Polytechnic University of Torino. So thank you, and please join us upstairs for the poster session. Thank you.